So far we have been looking at making one step TD predictions, right. So, what do we mean by that? It's essentially, if you look at the way we constructed the target, right, say TD0, right. So, when we constructed the target, we basically looked ahead one step, right. So, we get RT plus 1, which is the true reward, right, and then we look ahead one step and corrected that with the estimate of the value function from the second step onwards, right. So, instead of looking at the reward, actual reward you are going to get, we are using the estimate of the value function. So, that is basically what a one step algorithm. So, in the last videos you would have called it as one step Q learning also. The one step means you are not looking too far ahead into the future in terms of the real rewards, you are looking only one step into the future, getting the RT plus 1, and after that you are correcting for the future rewards by adding the value function, right. So, these kinds of things are called one step, right, truncated, because you stop here, and then corrected because you added the V to correct for the truncation. These are called one step truncated corrected returns. Okay. So, that is basically what it is. So, we will denote this with a superscript within brackets 1, which will mean that this is the one step truncated corrected return, and this is typically what we use in our TD0 algorithm or in our Q learning or SARSA. It is always the one step truncated return, right, a corrected return. Alternatively, obviously, so as soon as I say there is a one step return, then we can talk about n step returns, right. So, we can talk about n step returns, where instead of just truncating after one step, we truncate after n steps, right. So, since it is a return that we are looking at, discounted return, so we are going to get so RT plus 1 plus gamma, RT plus 2 plus gamma squared, RT plus 3, so on and so forth until gamma power n minus 1 RT plus n, right. So, that is essentially how many terms will go, and then we will correct it, right, by adding the value function of the state you encounter at time t plus n, right, after n time steps. What is the state that you will encounter at time t plus n? So, we will use the value function of that state and you will discount it by gamma power n. Why? Because that is that much far into the future, and your return is basically corrected by discounting with gamma power n, right. One thing to notice that it is still Vt, right. So, it is not Vt plus n of St plus n, right. So, it is still the estimate of the value function starting from the state that you will encounter at t plus n, right, but with the estimate that you have at time t, because you do not really have time to actually make all the updates when you are using this truncated return. So, to make an update to the V of St plus n, you would have had to go n more steps into the future before you can do that. Okay. Therefore, it is still a old estimate of St plus n. Okay. And so, once you plug that in, so you get an n step. So, basically you will get an n step TD algorithm, where you will use the correct return for n steps, right. You will use the correct sample of the return, you are not correct, you are not adding the value function to it, you use the correct sample of the return for n time steps, and for the n plus 1 time step onwards you will use the value function, and then of course, this is your new sample, right, and this is your old estimate. So, you have your old estimate plus alpha times new sample minus old estimate, and there you go. Okay. So, what is the advantage of doing an n step return? What is the advantage of using n step return for your predictions, right? So, if you think about it, the true return is essentially given by this thing, right, RT plus 1 plus gamma, RT plus 2 plus gamma square, RT plus 3, and so on and so forth. And the reason you are bootstrapping with the value function is so that you do not have to wait for a long time to make the updates, right. But the downside is your value function could be incorrect, right, and therefore, your return estimate could be incorrect, especially at the beginning of learning. Your return estimate can potentially be significantly incorrect because your value function estimates are wrong, right. So, you will be actually using the wrong target, right, when you are doing the updates. You will be using the wrong target when you are doing the updates, especially at the beginning of learning, right? When you're remember you starting off uniformly with everything 0 and so on and so forth, right? Now what happens if I do this, right? My correction term, right? So basically my VT plus n, right, which is the estimated, the bootstrapping term that I'm using, comes discounted with gamma power n, right? Comes discounted with gamma power n. So gamma is already less than 1, gamma power n will be much smaller than 1, and therefore you will be giving a lot less weightage to your existing estimates of the value function. So you will be reducing the error. I mean, if there is any error in the value function estimate, you will be reducing the error in the return estimate by discounting the value function estimate by a good amount, right? So that's good, right? I mean, you're trying to avoid the error, especially the beginning of learning. So what are the downsides of using an n-step return, right? So the downside of using an n-step return is, first thing, you have to wait for n steps before you can compute the return, right? So you can't do the update as soon as you come to ST. You'll have to remember at least n time steps. Just be talking about the problems with Monte Carlo. You have to remember the entire trajectory for you to make updates. Likewise, you have to remember at least n steps before you can make the update, right? In fact, the extreme case of this n step return is to do Monte Carlo, right? Monte Carlo will be to use the full return, right? So no correction at all, right? So that problem is there. And the second problem that comes in is because you are drawing a much larger sample here, right? So for n time steps you are looking at the return, there could be significant variance in the actual return that you sample, right? So if you are using the value function, right, so that's kind of an average over multiple returns, right? So that kind of reduces the variance already, right? But if you are actually drawing a sample from the distribution, especially if you are drawing a long sample, that means there are many different outcomes and the probability of each outcome is really tiny, right? In such a case, the variance can become very large, and so it can slow down the convergence. So there are these two trade-offs, right? So on one side, you have a better estimate of the return to begin with because it's an unbiased estimate, it's a true return sample. On the other hand, you have the variance becoming very high, and also that you have to wait for a long time before you can make the update, right? So there are ways of getting around this problem of waiting for a long time in a slightly funky way where we handle this multi-step returns, right? So let's look at how we do that. So here is an example of different kinds of multi-step returns that you could have. You could have one-step return, which is what we use for regular TD. You could have two-step TD, you could have three-step TD, n-step TD, and all the way up till Monte Carlo, right? So two-step, three-step, n-step, all the way up till Monte Carlo. Now, what step return that you should use? What is the right step return to use for your problem? Again, all the factors that I told you in terms of trade-off will be there. So sometimes you would like to use a shorter return, sometimes you like to use a longer return, right? So now this becomes like a hyperparameter that you have to tune, and it's not quite clear how would you do this. So you might have to come up with some empirical cross-validation procedure for figuring out what the right n should be, right? On the other hand, we have an approach, right, called TD-lambda, right, where we are going to use the following property, right. So consider this, right, instead of using a single n-step backup, right, just picking a value of n equal to 4, right, I will use only a 4-step backup, like we said, right, n equal to 1, we are using a 1-step backup, or we will use a 4-step backup, or we will use a 2-step backup. Instead of doing that, we can consider some kind of an average of these n-step backups also. So for example, here is one where I am taking half 2-step and half 4-step backup, right. So as long as I am actually doing a proper average of these different backups, right, some kind of a weighted combination, doesn't even have to be an average, right, some kind of a weighted combination. I mean, I can even use something like 0.8 times GT of 2 plus 0.2 times GT4, right. So I can do that also. I mean, so all of these, as long as it is a proper convex combination of these various length returns, it is still a valid estimate of my return, right. Does it make sense? So we say that GT2 is an estimate of GT, right, just like GT1, which is what we use. We argued that that is the estimate of GT because of the correction that we put in there, right. So normally your GT is right, and then we say that okay, GT of 1 is so that is an estimate of that. This is an estimate of that, right, and so likewise we have GT2 which is right. This is also an estimate of that, right. So likewise you can do that for other returns, right. We are saying all of these are essentially different ways of computing GT. We are not changing the definition of GT, right. They are all different ways of computing GT, and what I can do is I can do any combination of these n step returns, right, and that will also still be a way of computing GT. Okay, so that's fairly obvious, right. So I can choose some combination of this. Now, what combination do I choose? It turns out that in the 90s, people proposed something called the lambda return, right? They proposed something called the lambda return. So, where lambda is a hyperparameter, right? And the surprising thing is this basically combines all the n step returns, the 1 step return, the 2 step return, the 3 step return, all the way up to the Monte Carlo return. So it combines, right. So that is the idea behind lambda return. So it assigns, so lambda is a hyperparameter, then it assigns a weight of 1 minus lambda to the 1 step return. So if lambda is very large, then the 1 step return gets a very small weight. If lambda is very small, like 0.1 or something, then the 1 step return gets a weight of 0.9, right? And then the 2 step return gets a weight of 1 minus lambda into lambda, and the 3 step return gets a weight of lambda squared, and all the way up till the Monte Carlo return, which gets a weight of lambda power t, capital T minus small t minus 1, where this capital T is the length of episode, right, the total length of the episode. So capital T minus t, which is the where I start my computation from, minus 1, right. So GT lambda, this t is the t here, and minus 1, right. So that's the weight that you give to the full Monte Carlo return, right. So why is this a funny form? That's because once you reach the Monte Carlo return, all the further returns, right, suppose this takes you say 15 steps, right. So the 16 step return, the 17 step return, the 18 step return, and all that are basically the same value, right. You don't get any further rewards, right. Once you reach the terminal state, your rewards stop, right, and therefore the 16, 17, 18, 19 step returns and all that will be the same as the 15 step return. So the entire weight that you would give, right, going forward gets assigned to the Monte Carlo return. Okay, so that's why it gets this funny form. We'll see that in a bit, right. So the lambda return is written out like this. So it's 1 minus lambda, right, into n minus summation of n equal 1 to infinity lambda power n minus 1 GTn, right. So originally it's actually GT lambda is proportional to this sum, right. So that's how we wanted to define it. So I'm choosing a hyperparameter lambda. I'm going to use lambda power n minus 1 as the weightage for the 1 step return. So n equal to 1, so that will basically be 1. So I'm going to give a weight of 1 for the n step return, 1 step return, and a weightage of lambda for the 2 step return, lambda squared for the 3 step return, and so on and so forth, right. So that is how I initially started. Why the proportionality sign? Because the scaling factors have to sum to 1, correct. The scaling factors have to sum to 1, only then it's a correct estimate of the return, like we saw here, right. The scaling factors have to sum to 1, and therefore what will be the constant of proportionality here? So it's basically summation n equal 1 to infinity lambda power n minus 1, which is equal to, right. Therefore I multiply by 1 minus lambda, okay. right. Is it clear? So, that is how I get this funny weighting form, right. So, initially I just say that I am going to weight each return by lambda power n minus 1 and then sum over all possible returns, right. And then to kind of normalize the sum to make it into a proper weighted combination, I divide by the overall weight of the coefficients, right. So, that basically gives me this. Therefore, the one step return gets a 1 minus lambda. Okay. So, what happens in this final case is the following. Let us say that you run all the way up till time step t, right. So, I can write it like this. Okay. So, suppose it is an episodic task and the episode ends at capital T, I can write it like this, right. So, this goes from n equal 1 to t minus 1 lambda power n minus 1 into GTN, and from n equal to t onwards, because at t the episode ended, right. So, I actually get the true return. It is no longer the n step return or anything, it is actually GT, right, that is there, right. So, since this is GT, so this term alone I am now writing, right. So, this term alone I am writing here. So, this is equal to GT into 1 minus lambda into summation n equal t to infinity lambda power n minus 1, right. Right. And this I can simplify as GT into lambda power t minus 1 into 1 minus lambda into summation, right, and this is equal to, because this is equal to 1 by 1 minus lambda, this and this will get cancelled. So, this is equal to GT into lambda power. Okay. So, that basically becomes the weight for GT. GT is the final return. So, that becomes the weight for GT. Okay. Okay. So, that is how we get the final return, right. So, now that we have this, right, we can think about what happens. So, if I set lambda equal to 0, if I set lambda equal to 0, right, my GT lambda is equal to GT1, right. If I set lambda equal to 0, what happens? So, everything else becomes 0 and all the weight, basically weight of 1 falls on the one step return. So, if lambda equal to 0, GT lambda becomes GT1, right, and likewise if lambda equal to 1, GT lambda becomes, if lambda equal to 1, this is 0 0 0 0, but that will not be 0, that will be 1. So, it becomes GT, right. So, now in the TD lambda case, when I put lambda equal to 0, I get my one step TD, and if I put lambda equal to 1, I get Monte Carlo, right. So, the TD return is essentially gives me this way of spanning an entire dimension. So, when lambda equal to 0, I have my usual one step return or whatever we have been discussing so far as TD, and when lambda equal to 1, I get my Monte Carlo return, which we talked about earlier, right. So, this lambda allows me to go between one step TD to Monte Carlo smoothly, and in between for any intermediate value of lambda, it becomes then a weighted combination of all possible n step returns, including the full return, right. So, that is the idea behind TD lambda. So, why did we propose this kind of a weird summation, right. So, why did we choose lambda power n minus 1? It turns out that that is a nice reason for that. Because this allows you to come up with a very efficient implementation of this lambda return, right. So, you can use this algorithm that allows you to do this efficient implementation of this average of n step returns, right. And in fact, the efficient implementation is what came first, right. And then people saw what that efficient implementation was computing, and then they came up with this definition of lambda return. So, it was not quite this way, because there is a different motivation for the implementation. So, we will look at that, right. So, this is called eligibility trace, right. So, sometimes so this is called the forward view of TD-lambda. Right, forward view of TD-lambda, and this is called the backward view, right. So, it is called the backward view because at any time t, you are going to look back and decide what updates you are going to make to v of st, while in this case at any time t, you are going to look forward to an n step return and then compute the n step return and use that to update the state t. So, this is the difference between the forward and the backward view, right. So, the backward view is essentially something where we use this notion of what are called eligibility traces, right. So, the idea of eligibility trace comes from again psychology literature. So, where people were looking at the following: suppose a particular reward, right, particular payoff happens at a specific time, right. It's a particular payoff. I mean, it could be a positive thing, could be a negative thing, right. So, which of the past sensations or past decisions that I have made are eligible to receive credit for this reward? That makes sense. So, at time t, I get a reward, right. I look back and I try to make a guess for what are all the events that have happened in the past, right, that are eligible for getting the credit for this reward, right. I mean, reward, punishment, whatever it is, but they are the events in the past that take credit for this, right. So, one way that people thought of was, okay, things that are temporarily very far away. Suppose I get the reward at time 10, so something that happened at time 1 is most likely not the cause, right. It's probably something that happened closer in time to the event, right. Maybe not just the last bit, but maybe something that was leading up to that, right. So, what people said is, okay, as soon as an event happens, let us say the event happened here, right. So, it becomes eligible to receive any future rewards that is going to come, and as time goes by, the eligibility for getting the reward is going to decrease. So, if the reward happens, let us say the reward happens at some point in the future, then this state is no longer eligible because it has decayed off, the eligibility has decayed, right. So, if we can, so that is the idea behind eligibility traces, right. So, the closer in time an event is to the final reward, right. An event here is some occurrence, right, some action or some state that you have seen in the past and so on and so forth, right. So, that event is eligible to receive some portion of the reward, assuming that it is close enough in time to that event. I mean, it is not a perfect assumption, but that is something that you make to get these eligibility traces to work. But the meta idea behind eligibility traces is you want to have some way of determining what are the things that happened in the past, right, are eligible for a portion of the reward now, right, or taking a credit for the reward now. That is why it is called a backward view, right. It's called a backward view because you are actually looking behind and seeing which ones are eligible, right. So, the idea here is now to do something as follows, right. So, you maintain a variable called an eligibility, right, for each state that you are encountering, right. So, you are going to maintain the eligibility for each state that you are encountering. So, you add 1 to the eligibility, right, if a state occurs at time t, you add 1 to the eligibility if the state occurs at time t. If the otherwise, right, what you do is you take the old eligibility that you have, the et minus 1, and you kind of decay it a little bit, right. And since we are using lambda as our hyperparameter, so we are going to decay it by some factor of lambda. So, it turns out that the right way to decay this is something called is gamma lambda, right. The right way to decay this is to use gamma lambda, not just lambda, but the discount factor gamma also, so that as we will see in the next slide, the next couple of slides, what updates you compute using the algorithm which we call as TD-lambda algorithm is exactly equivalent to the lambda return. So, for that to happen, right, so remember what the lambda returns are. Lambda returns are this, right. So, GTN weighted by lambda power n minus 1, right, and gt has its own thing. So, gtn will have rt plus 1 plus gamma rt plus 2, so on and so forth for n time step. So, because of that you have to worry about the gamma also coming into the picture, right. So, it turns out that so you have to discount by gamma lambda, you have to discount decay the eligibility trace by gamma lambda if s is not equal to st. If s equal to st, what does it mean? If the at time t the state s actually occurred, then the eligibility of s is also decayed from the previous time step, but you also add a 1 to it, right. So, these are called accumulating eligibility traces, so that you can see that so this is eligibility trace for some one state s, right. So, you visit state s and this is over time, right. So, here you visit state s, let us say t equal to 1, you visit state s, then the eligibility goes up and then it starts decaying, right. At some other point t plus k, you visit s again the eligibility goes up by 1 more. So, you can see that the eligibility is actually racking up quite a big bit, right. And so, if a reward occurs here, then state s is very eligible to get an update for the reward, but if a reward occurs here, right, you are going to assume that that state s is no longer that eligible for the reward, okay. And you keep doing this is called accumulating eligibility trace. You could also define something called replacing eligibility trace, where the equations are very similar, this is the same, but here it is just 1 if s equal to st, right. So, instead of carrying over the previous eligibility, you will just replace it by 1. So, what will happen in this particular instance, right. So, it went up to 1 and it starts decaying, the state happens here again, right. So, it will basically go back up to 1 and it will start decaying, then it will go back up to 1 and it will start decaying, go back up to 1 and it will start decaying, and it will go to 0 already, right, and it will stay at 0 and then again it will go back up to 1, start decaying, go back up to 1, start decaying and then go to 0. Right. So, this whatever I have drawn in red is the replacing eligibility trace. So, sometimes people say you should use accumulating eligibility trace for certain kinds of computation. Sometimes you use replacing eligibility trace because otherwise sometimes what happens is a state can become very eligible, right. If you basically repeatedly visit the same state many times, and then you get the reward only when you break out of the loop, right. So, the state that was right next to the reward might be less eligible for the reward than a state that was far away from the reward, but got visited many times in a loop. To avoid situations like that, people suggested using replacing traces. So, and when you are implementing something, you have to take a call, right. Accumulating traces are better typically, but you might want to use replacing traces also. Accumulating traces are somewhat equivalent to every visit Monte Carlo, while replacing traces are equivalent to first visit Monte Carlo, if you want to think about it. I am not going to get into all of that details. We have some videos that you can watch as a supplementary material, not as part of the course, that talk about many of these issues, right. So, putting these things together, let us talk about the TD-lambda algorithm, right. So, the TD-lambda algorithm works like this, right. So, you start off with as usual, you initialize V of s arbitrarily and you initialize the eligibility to 0 for all states, right. And then for each episode you start off s and repeat for each step of the episode, right. A is the action given by pi, whatever, right. Pick an action A in state s. Remember it's TD-lambda, right. So, that means it's an evaluation thing, right. So, that means your pi is fixed, right. And then take an action A, observe the reward and the next state, then you compute the TD error, right. This is called the TD error, right. So, this is the TD error. Compute the TD error, which is r plus gamma Vs prime minus V of s, right. So, this you know, right. Then what you do is you increase the eligibility by 1, right, increase the eligibility by 1. So, because that is the state now you have visited, right. So, the eligibility has to go up by 1 and then you update the value function using this expression, right. Update the value function using alpha times, which is the step size, alpha times delta. So, the normal TD0 update is just stops with alpha times delta, right. V of s equal to V of s plus alpha delta is their normal TD update. But here what you do is you use V of s equal to V of s plus alpha delta E of s, which is the eligibility of the state. Okay. So, that is the first thing that you have, right. So, the normal TD, I will just write what TD0 will look like, right. TD0 will be, right, V of s right, that will be TD0, and you will be doing this only for the current S. Right. But with TD-lambda you do this for all S. TD-lambda you do this for all S, for all the states you do this. Technically you have to do this only for those states for which the eligibility is non-zero, but implementation wise it might just be convenient for you to do this for all S, unless you have a efficient data structures that can keep track of what are all the states for which the eligibility is non-zero. I mean, you can think of creating a data structure like this, right. And then what you do is you decay the eligibility trace, right. Why are you decaying the eligibility trace after you do the update? Right. Why are you decaying the eligibility trace after you do the update? You are not really using it for this update, but you are decaying it for the next update. Remember that for all S you will have to decay it whether the S occurs or not. So, you actually pre-decay the eligibility trace and then you go back and you add one to the state that actually occurred, right. So, this is basically how you handle it, right. Okay, and suppose you want to do replacing trace instead of accumulating trace, you will say E of s this one. This is for replacing traces, right. This is accumulating. Okay, makes sense. You repeat this until S is terminal, and then when you restart the episode, you actually have to reset the eligibility to 0 for all the states. So, that is kind of should come here. Because eligibility does not carry over from one episode to the next, right. Once you reach the end of the episode, all your eligibility gets set to 0. Okay. So, that is basically the TD-lambda algorithm, and now you have to take it on faith when I say that TD-lambda, the forward and the backward view are actually computing the same update at the end of the trajectory. If you make the backward view, if you accumulate all the backward view updates, do not make it while the episode is running, right. So, compute all the changes that you will make to the V, right, and then at the end of the episode make everything in one go. And if you had computed the lambda return and then made all the updates at the end of the episode, right, you will get exactly the same updates. So, the forward and backward view are actually equivalent, and it is not very hard to show, it is just a little bit of bookkeeping. You have to count very carefully how many times you are changing each state and by what delta you are changing each state. And so, once you compute that, you can see that the forward and backward view are same, and it is there in the supplementary material. I encourage you to look at it just so convince yourself that the forward and backward view are the same. Okay. So, the TD-lambda algorithm is fairly straightforward to implement, and it turns out that if you are not using function approximators, if you are not using things like a neural network, then the TD-lambda algorithm is fairly straightforward to implement. And when I start using a neural network for representing these things, then it becomes a little tricky, right. So, it is not entirely clear how would I implement the TD-lambda algorithm efficiently, right. I mean, implementing it somehow is fine, but doing it in a manner that actually allows me to run large experiments in a bounded time becomes hard, right. So, people typically do not use these eligibility traces a whole lot with the current implementations, but I still think it is a very powerful technique. And so, eventually you should I mean, if you can figure out a way to use this more effectively, then more power to you with neural networks. But even then, in the non-neural network setting, these eligibility trace ideas are useful, right. So, one other thing I want you to note about the TD-lambda algorithm, it's actually a very powerful idea, this idea of eligibility traces, right. So, notice that this algorithm does not make any assumptions about what is the value of lambda, right. I said like if lambda is 0, then you will make this update only for the current state because everything else will decay to 0, right. But what happens when lambda equal to 1, right? When lambda equal to 1, this algorithm will work fine, right? There is no problem with algorithm, right. So, basically what will happen is this gamma lambda ES will just become gamma ES, right. So, the eligibility will decay only by whatever value of gamma that you use, right? And the lambda part will not play a role in the decay, right. When lambda equal to 1, this will be just E of S will be but what do we know about the lambda return when lambda equal to 1? Lambda equal to 1, this implies that what I am doing is Monte Carlo, right. I am doing Monte Carlo updates. So, one of the disadvantages we said of doing Monte Carlo updates is that you have to wait till the trajectory ends before you can actually do the update, right. So, that means that you have to store a lot of transitions, right, and then come back and do the update for all the states in one go. But remember, the TD-lambda algorithm is actually incremental, right. So, as soon as you make a step, you compute the delta, right, and then you use that to change your value function for all the states which have a non-zero eligibility, right, and then you are done, right, and then you just go back and get the next delta. So, you do not have to actually wait till the end of the trajectory to compute your lambda return and make the update, right. So, that is the biggest advantage of the TD-lambda eligibility trace idea. So, that applies to lambda equal to 1 case also. That means that you can now implement Monte Carlo without having to wait till the end of the episode to compute the return, right. Of course, there are small caveats to it. I mean, you can watch the forward backward view equivalence video to understand the caveat, but this is a very powerful thing, right. Now, I can implement Monte Carlo can be implemented incrementally. So, one of the biggest advantages of using eligibility traces is something like this, right. Suppose there is a trajectory and then you get to the goal by going through this pathway. If I am using my regular SARSA or my one step SARSA as we call it, then only this Q value will get updated, right. But if I am going to use an eligibility trace, right, remember like SARSA uses TD-lambda for updation, right. So, like that if I use a TD0 for updation, I can use a TD-lambda like update for SARSA, then what will happen is all these states, right, because everything has some eligibility going forward, right. So, because of that, so even the Q value here will have some non-zero eligibility of receiving an update. So, as soon as you do one trajectory, so many Q values get updated. So, you can learn much faster in terms of the number of trajectories that you need to learn, right. So, here is another example of TD0 versus TD-lambda. So, here I am starting off with a simple grid world, right, and so you can see that all the states that are marked in red have a reward of -1, right. The state that is marked in green has a reward of +1. These are obstacles and the other states do not have any reward, right. Okay. So, now this is a demo that we stole from Andre Karpathy's web page, but you can go to the web page, you can see the URL here. You can go to the web page and actually play around with this demo. You can change the grid world around, you can look at different algorithms, different values of lambda and so on and so forth, right. And so, here is what happens when you set lambda equal to 0, right, alpha equal to 0.1, it takes a good number of steps, right, before it reaches the goal, right. And so, this happens when lambda equal to 0.8, right. So, you can see that it reaches the goal much faster, right, and you can see by now by the time you reach 200 actions, most of the actions now have a positive reward. That means that you have basically learned how to go to the goal without hitting the obstacles, right. So, you can see when lambda equal to 0, right, it takes a while for you to start reaching the goal quickly, and by the time you get here, right, in the 200th episode, you still have only a few states for which you know how to get to the goal without getting a negative reward, right. While here you have learned that for a large number of states already.